Hi guys, my name is Alex Davies and this is my master's project presentation for the Bristol Data Science Masters. And I'm hoping that 10 minutes can start now. In astronomy, there's two broad schools, spectroscopy and photometry. Spectroscopy is much higher resolution in terms of information you can gain about an object, but is much more intensive. You need much longer exposure times and more complex apparatus. By contrast, photometry is less precise, but you can image multiple objects at once and they require shorter exposure times in general. Here we use photometry as a catalog. The catalog we use as a fully labeled set was constructed by Fotopoulou and Paltani in 2018. They use random forest classifiers to split between different classes of astronomical objects to improve photometric redshift estimates. We also build upon the work of Logan and Fotopoulou in 2020. They use an unsupervised classifier pipeline based upon PCA and HDBSCAN to classify between stars, galaxies, and QSOs. They also update the previous data from Fotopoulou and Paltani 2018 to create a dataset of 2.7 million objects, but without reliable spectroscopic labels, i.e. an unlabeled dataset. The pipeline we design is principally for partially labeled datasets. We pipe UMAP into HDBSCAN and then assign cluster labels using the majority of each cluster. Again, this is a very brief explanation. Please do have a look at the report document. We also test whether our pipeline can be applied to across data spaces and with much larger data sets. The essential methods for a partially labeled dataset are either to fit to the whole dataset with the UMAP embedding or fit to only some subset of it, say the labeled objects within that dataset. If you want to classify wholly unlabeled new data, you can either attach a labeled dataset to that new data, or you use a pre-fit embedding, fit to a dataset you understand well, train a supervised classifier on that embedding, project the new data, and use a supervised classifier to determine what the points in that are. We avoid doing this as this would not be an unsupervised problem, and it carries all the biases that come with unreliable labels and so on. I'm not going to go into the algorithm too much. The whole pipeline is here. Feel free to pause or again have a look at the document. The only thing that's really important to note is that we construct color attributes from our magnitude data from our photometry, which is this magnitude 1 minus magnitude 2 for every non-redundant combination. So we have magnitude 1 minus magnitude 2, but not magnitude 2 minus magnitude 1. We can measure performance through a four-fold validation using the fully labeled dataset. We do this by fitting the embedding either to the whole of that data or only to the training set of that data, and then applying HDBSCAN to the test set each time. We do consider including secondary attributes alongside, but we find that these only decrease in performance. The attributes we would include were found using a random forest classifier through the feature importances attribute that the sklearn distribution has. These attributes are presented on the right for each class. Our results for labeled data were good. They matched those of Fotopoulou and Paltani, Logan and Fotopoulou 2020. You can see that for stars we actually exceed their results, but we get very similar results to them in terms of QSO performance. When we try applying an embedding fit to the training set to the test set, we get results like this on the right. Obviously very protracted clusters, very spread out. They do not really resemble the embeddings used to create them. We alleviate this issue by transforming the data in batches instead, resulting in embeddings like the one on the right here. The results here aren't as good as when we fit to the whole data. This makes sense. The embedding can't represent as much of the data if it hasn't been presented with as much of the data to be fit to. The strings you see, the outlier points, I believe they're due to points that lie outside of the data ranges in the data that the embedding was initially fit to. In comparison, it's better to essentially fit to the whole data set. This is intuitive, but we have demonstrated that it is possible to use a pre-fit embedding within the same data space. As you can see, we get very similar results to Fotopoulou and Paltani, Logan and Fotopoulou 2020. Please do go have a look at their results precisely. I don't have time to summarize them here, but we need to investigate why the same proportion of QSOs are labeled as galaxies in our work and theirs. To do this, we use a random forest classifier without UMAP as an attribute. We use the outer bound scores for each point to work out the probability that each point, when predicted by trees within the forest that have not been exposed to that point before, will predict it wrong. You can see there's a definite uptick towards the probability of incorrection being 1, and the histogram on the right there. You can also see that in our UMAP embedding, we have some points that are in the wrong cluster. We use SDSS, the Sloan Digital Sky Survey, to source spectra for each object, and we present them here. On the left-hand side is a well-classified galaxy, And on the right-hand side is a poorly classified galaxy. You can see the spectra are very similar, but the magnitude data is quite different, with a disconnect at about 10 to the 4 angstroms when we change which survey the data is sourced from. You can see that we've fairly well picked out the points that are in the wrong cluster using this random forest classifier. This is encouraging because, again, UMAP has not been an input attribute, which means that the random forest classifier is finding the same thing, but it may just be finding the same issues in the data that are represented by the UMAP embedding and found by the random forest classifier. The results for the clean data are predictably better, and again, better for fitting to the whole data set, but this isn't necessarily evidence of an improved classifier, only of a cleaner data set. We now try fitting an embedding to the whole of the 2.7 million point data set. We again source from the Sloan Digital Sky Survey spectroscopic labels for about 1% of the data, which is the colorful points you can see scattered on that 2D histogram on the right. These embeddings are stable across a wide range of hyperparameters from n neighbors equals 50 to n neighbors equal 1,000. We choose n neighbors equal 100 as that's what we use for the fitting to the labeled data set. The important thing to note here is that stars are well separated from the other two classes, but QSOs and galaxies appear in the same cluster, and indeed HDBSCAN also finds them to be in the same cluster. We experiment with re-embedding the points. On the left-hand side of those original points that are labeled as galaxies, we take a 500,000 point sample from that so that we can run it locally. We re-embed, which is that second plot. Color here indicates density. And the next plot, you can see where the points are and what they are. You can see the QSOs are slightly more separated from galaxies than they were in our initial embedding, but not perfectly. And indeed, when we apply HDBSCAN, does separate them. But this does show promise as an area of future research, especially with fine hyperparameter tuning. When we experiment applying stuff between data spaces, we fit an embedding to the fully labeled FP18 data set and then apply it to that much larger LF20 data. This is on a 1 million point sample from that data. You can see the clusters do not represent one single class as they did in our previous embeddings, and they're much more protracted and don't really resemble the original embedding used to project this data. This is likely symptomatic of our use of a projection between data spaces, where measurements are different and apparatus is indeed different, given that we've sourced from different surveys. We also attempt attaching a labeled data set to an unlabeled data set. So this is the full FP18 labeled data set attached to 1 million points from the LF20 unlabeled data set. On the right-hand side, you can see this is the overall embedding with the labels from FP18 scattered. On the left-hand side, we separate the two, and you can see that the points do not lie in the same clusters. In fact, it seems like an LF20 embedding overlaid with some extra clusters due to the FP18 data. Even when they are within the same cluster, they don't represent the same, they're not in the same places in the cluster. Again, likely symptomatic of our use of data in between data spaces for our embedding here. Overall, the lessons learned are that this classifier does show promise. It functioned well on the fully labeled data set, but we do suffer from this data being sourced from multiple sources and multiple surveys. You can see the disconnect there is quite pronounced at 10 to the 4 angstroms. We also note that issues within the data for these consistently mislabeled points are also likely due to this and have been represented by the UMAP embedding. I'd be intrigued to see what future research can do using data from, say, the upcoming Euclid mission, where it's one survey providing full photometry coverage across multiple wavelengths instead of having to source from multiple surveys. Applying prefit embeddings works within the same data space, but not cross data spaces. And the same thing is true of attaching a data set. I'd advise only using this pipeline if you're working in the same data space. Re-embedding is also a good area of future research, especially with fine-tuning. In general, long summer projects are quite hard to do if you quite like holidays. I did manage to get away, I went cycling, but it did mean I have to work very hard in between. I found that unsupervised learning is much less intuitive to interpret than supervised learning, simply due to the complexity of it. Data from multiple sources is hard to work with, and finding mislabeled points is a harder endeavor than you might think. Working with Dr. Fotopoulou, although fantastic, did put more pressure on, as it's easier to let yourself down than somebody who's actually interested in what you're doing. Future work could focus on using TSNE. You can see an embedding there on the right that we've produced. That's with perplexity of 1,000. The runtimes are much longer, but you can see it does separate QSOs from galaxies. Part of the reason we use UMAP is because it is more visually intuitive. You can interpret it better, but TSNE as part of a classifier might be more appropriate. You could also experiment with the same approach to embeddings as in Logan Fotopoulou 2020, when they embed only the most important attributes for each class. In our GitHub repo, we do include an sklearn style classifier for rapid testing, as well as the full pipeline and classes that we used in our research. Fantastic. Thank you.